All right, so example number 2, is that all right? We move on to another example. Okay, just give me 1 second, okay? Let me just take care of one thing. All right, so example number 2 is, let's look at an example of an irreversible process, okay? So an example of an change of entropy in an irreversible process. So the example that we have is, we have a gas, an ideal gas, in some sort of box with some specific volume, in a little sort of pipe that leads to another identical chamber, and there is some sort of stopgap here, stopping the gas from escaping. So this has, the gas has pressure V0, P0, and it's got volume V0, and so this gas is a over here. Okay. Oh, sorry, I didn't mean that. So the gas just goes up to here. Okay, so this is not a perfect drawing, but you know what I mean. So we're also assuming that this is a container which shields the gas thermally. It's isolates it from the rest of the world, so heat cannot come in or go out. Now, suppose that we allow we open the tap for a brief moment. Well, we open the tap so that the gas can now leak into the other chamber, quite rapidly. So this is scenario 1. And after that, what happens is that we are just going to let the gas out. Copy, paste. And now the gas is everywhere. Okay. And it should be clear that this is not a reversible process, right? Because you cannot suck in the gas, just by, this was quite a sudden change. Now, the idea is that, what happened, so we can now ask the question, what is the change in entropy? So before we do that, let's look at our other parameters that specify our state. So now the pressure is PF and the volume is twice as much. Okay. Now, here's a case where, when we actually opened this this tap, before the gas leaked out and created another equilibrium state, there was no equilibrium in between, right? So so the idea of pressure, talking about pressure in between, would be completely meaningless. In other words, we cannot use the first law to track the change in its energy, right? Internal energy. Remember that the internal energy is something like du is T ds minus P of dV. So this is a small incremental change. But here, P is not defined. So we are not going to use this to figure out the internal energy. Instead, what we're going to say is that, well, this system is isolated and we have not done any work on it. So no heat has flowed in and no work has been done on the system. And therefore, the internal energy of the system must be the same. And therefore, the internal energy is the change in internal energy is 0, okay? We're also assuming that this is an ideal gas, and we know that the ideal gas internal energy is something, depending on, for 1 mole or something, it's something like 3/2. What is it? RT? Something, yeah.
Sir, I couldn't follow. Why was the internal energy not changed in this case?
Because no work was done on it and no heat was exchanged with the environment.
Oh, right.
Okay. So, but the internal energy is just a function of temperature, and therefore we can say that the change in the temperature through this process is also 0. In other words, we can say that Ti is equal to Tf, or T0 is equal to Tf. Okay? So now if I use the ideal gas law, that means that the pressure, final pressure, must be equal to the initial pressure divided by 2, because the volume has doubled. But the PV is RT, right? So T is the same. V has doubled, therefore P must halve. Okay, is that clear?
Yes, sir.
Okay, good. So then what we can do is that we can say, okay, what is the change in the entropy? The change in the entropy from the initial entropy to the final entropy is d of s. Now, there is no obvious way for us to measure this entropy, right? So what we can do is that we can say, okay, what if we had an identical system, but instead of turning on the valve, so that gas just flows in suddenly, we just allow a little bit of gas out, one at a time, at a time, so that the whole system remains at equilibrium. Basically, what if we did this quasi-statically? Or we could have just done something more where we can just like crank up or come up with a scenario where this could be done even reversibly. So the idea is that we compute the entropy using such a, so basically, what happened is this: we have our state space, and we went from, say, here to here in a way which is not reversible. There is not even a path, but we find some way of going from this point to this point in a reversible way. Okay? It doesn't matter what that reversible way is, but we just find something to calculate. It could be, it could be some idealized process, right? And then if such a process exists, then according to, because this change is adiabatic, the change in entropy, well, because we are saying d of u, so d of u is sorry, let me just see. Yeah, sorry. So we're looking for state in which d of u is 0, and therefore what we have is d of s is equal to p of dv divided by t. And therefore, we can use that to write this as p of dv divided by t. And then v goes from, say, v0 to 2v0. But what is p? P is r times t over v, and there's a t before, dv. So now, so if you now integrate this, it's just r times the log of 2, or 2v0 by v0, and these cancel out, and this is r of log of 2, okay? So this is basically how we calculate the entropy of an irreversible process by finding a path in the state space which connects those same 2 points, but using a reversible path. All right, so why can we do this? Because entropy is a state function, or a function of state. So it's a function of state. So even if we are trying to calculate the change in entropy between 2 equilibrium states which are connected by an irreversible path, we can do this because it doesn't depend on what path we took between them, and we found a path which was reversible, and we could therefore do an analytic calculation. Okay, so this is a kind of a subtle idea, but this is basically what I'm. Okay, any questions?